Oh, hey, Leonardo. Great to see you. Welcome. Yeah, yeah. I went much slower than I anticipated, so I'm like a lecture behind already.
I've never heard a TASI lecture run out of material.
Yeah. Yes, yes. Thank you.
All right. Well, yes, I greeted Mr. Estelle. Sure. So our last scientific organizer has arrived, Professor Leonardo Estelle. Say hi to him if you don't know him already, or you can say hi to him if you do know him already. So we're going to continue with Ken Intriligator, talking about supersymmetry, renormalization group flows, and stuff like that.
Thank you. Okay, so I'll continue with SUSY QCD and duality. And first I just wanted to say kind of a little bit generally that's where I had this picture in the beginning of flowing from the UV to the infrared with some kind of deformations like the gauge coupling, or we could consider other kinds of deformations. So we start with some UV theory and then we can deform it. And in the context of supersymmetric QCD, two deformations that I especially want to consider are mass terms and expectation values along this moduli space. And so maybe I'll write it here. We could consider mass deformations For example, I could add a superpotential, which is a mass term for one of the flavors. Let's say the last flavor. So NF tilde. So this is a mass term, and this is this meson operator, which is Q tilde that I introduced, that I discussed in the last couple of lectures, and that's there on the table. And this kind of mass deformation, it induces a renormalization group flow like this, where the effect of the flow is in the ultraviolet, we have NF flavors, and then in the infrared, we decouple one of those flavors, and we have NF minus 1 flavors. So in the case of the mass terms, we can have a RG flow where, let's write it like this. We start off with a theory with NC colors and NF flavors, and then we give a mass to one of the flavors, and we still have NC colors, but we have NF minus 1 flavors. And so there's some kind of, if we plot as a function of energy scale, let's say here this is the flavor that we've decoupled. Up here we have NF flavors, down here we have NF minus 1 flavors. And now what we could do is we could match the running gauge coupling across that threshold. So everywhere, so up here we have, let's write it this way, e to the minus 8 pi squared over g squared as a function of mu is lambda over mu to the one loop beta function. And the one loop beta function up here is 3nc minus NF. And then down here we have NF minus 1 flavors. So we do the same thing. Let's say here we have some lambda low. NC minus NF minus 1. Now, the theory in this case that we have in the infrared is more asymptotically free. There are fewer flavors, so it's more asymptotically free. The beta function makes the gauge coupling want to go towards stronger coupling in the infrared. And so here the effect of this is that our infrared theory is stronger than it would have been without the mass term. And so here we get a theory that's stronger in the infrared. And we could see that if we match these running gauge coupling at the scale mu, so here I'm going to set mu to be equal to m and set these things equal to each other. And so then what I see is that lambda low is the mass term that we added. So if this mass is big, then we could see that this lambda low is going to be kind of bigger than the lambda of the original theory. And so that's what I mean by saying that the low energy theory in this case is more strongly coupled.
What happens is that how they do things in QCD?
Yeah, we could do the same kind of threshold matching.
What people do when they come down, through the bottom port to the charm port,
There are different scheme choices that you can use with how you. Okay. Yes. So the question was if this is what people actually do in QCD, and so here there's some scheme choices that are hidden in how I'm defining the dynamical scale lambda, and so sometimes people like to take some like mass independent schemes and. There are various different choices, MS bar, things like this. For our purposes, this is the most convenient way to do it, and it could also be done in QCD, but there's some kind of choice. The nice thing here with this choice is that we're looking to find the dependence on these quantities, and we could get exact results from supersymmetry because for quantities that are holomorphic. And the reason, again, is because we could think about the coupling constants as also being expectation values of some chiral superfields. And then anything that depends on chiral superfields in a way that's constrained by supersymmetry, like the superpotential, has to be only depending on the chiral superfields, not the anti-chiral superfields. And so things have to be holomorphic in the fields and the coupling constants. And so we're going to think about these as all being actually complex quantities, and everything will be holomorphic in these complex quantities. So even though I didn't, just to say a little bit about the phase, I didn't write it here, but there's also a plus I theta, which I didn't write for lack of room. And this thing also works for the theta angle, because the M dependence, if it has a complex phase, you could put that into a phase rotation of the fermions, and that amounts to shifting the theta angle. And so this thing here is all holomorphic. In these complex quantities, and that's a real that's a powerful tool in supersymmetry, but in ordinary QCD you wouldn't use that. Okay, so this is one deformation that we'll be interested in. The other kind of deformation that we can do is expectation values, which is moving on this moduli space of vacua. So this is vacuum expectation value for some matter fields, and an interpretation of this that I discussed last time is that this is associated with Higgsing. So for example, we could give an expectation value to the meson operator, to one component of this meson operator. And so this is the same operator that appeared here. And the effect of that, just like over here, is to take the theory with NC and NF flavors. And then what we get is a theory with NC minus 1 colors and NF minus 1 flavors, plus some decoupled free moduli. Like, for example, one of the decoupled free moduli is this thing itself, and also the meson operator is built up out of that last flavor. So that last flavor, the last flavor that we decoupled, it's gone, but some of its meson operators are still there, and that's here. And so again, we can draw a similar kind of picture where, as a function of the energy scale, we have here some expectation value for the fields Q and Q tilde. And above that scale, we have the theory with NC colors and NF flavors. And then below that scale, we have the theory with NC minus 1 colors and NF minus 1 flavors. And again, we can match this running gauge coupling. And so if we match the running gauge coupling, we'll see up here, we have lambda to the 3 NC minus NF. And down here, we have lambda low to the 3 NC minus 1 minus NF minus 1. And in both of the cases, e to the minus 8 pi squared over g squared runs with this divided by mu, and then we need to match these. And so the way that we match them is we match them at the scale of this expectation value. And so now this scale of this expectation value is basically like the square root of this m. M is q tilde. And so we're matching at an energy scale that's set by m. And so if we just count here, we'll see that there's, if we just use, we could basically just use dimensional analysis to see how it works. 3 NC minus NF divided by m. So if we just use dimensional analysis, m has dimension 2, and this thing differs by mass dimension 2 from the other side, and so now the units work. And this is just what we would get if we match the running gauge coupling across the two thresholds. And again, this is nice because it's holomorphic. And what we can see from here is that here I said the infrared theory is more strongly coupled. Here the infrared theory is less asymptotically free. The fact that this thing went down by 1, this thing went down by 1, and this thing went down by 1, but this had a 3. So here the infrared theory is less asymptotically free. In fact, if you do this enough, sometimes you could get a theory where all the gauge fields are gone if we have enough flavors to keep going along this track and completely Higgs the gauge group. All of the gauge fields can be gone. And then the theory would just be a decoupled theory of free moduli. But even if there are some remaining gauge fields, the theory is less asymptotically free. And sometimes it could even not be asymptotically free at all. And we could see that here because if this m gets big, then this lambda low is smaller than this lambda. And so the theory is less asymptotically free. So these two are kind of opposite to each other. One takes us to stronger coupling and one takes us to weaker coupling. And in the context of Seiberg duality, which I'll discuss later, these things will be interchanged. And so this often happens in dualities, is that you exchange something that's strongly coupled with something that's more weakly coupled. Here these two deformations will be exchanged. One takes us to stronger coupling and one takes us to weaker coupling, but it'll be matched in different ways across the duals. Okay, so last time I discussed the theory with NF equals 0 and mentioned that there's this superpotential which we can write like NC like that, and derivatives of this with respect to log lambda give d by d log of lambda to the 3 NC of this W gives the expectation value of this glue ball operator S. So S again is lambda alpha. It's the Gaugino condensation, Gaugino bilinear. And so this represents Gaugino condensation. Now, we could immediately use this result for the theory with NF massive flavors. So suppose we have general NF massive flavors. So if they're NF massive flavors, the theory in the far infrared, if they're all massive, will be this theory. There will be no flavors left in the infrared because we've given masses to them all. So we could now use this result, and I'll just write this as lambda low. That's the low energy theory where all of the flavors are massive. And now what I'll do is I'll say that lambda low, just using this thing over here, to the 3 NC is the determinant of the mass matrix that we've added times lambda to the 3 NC minus NF. And so we could just plug that in here. And so we see that W of the low energy theory is NC determinant of the mass matrix and the physics of this again is that we have NC SUSY vacua. They have a mass gap, confinement, and they have this expectation value of S, which we could again write as the derivative of this W low Okay, so if you want, you could work out what that derivative is to get the expectation value of S in the low energy vacuum. And we can also say what the expectation values of the Meson operators are. because again, this mass term, we could think about it as a source for this operator. And so the way that we get expectation values of the operators, we take a derivative of the we take a derivative of the effective action as with respect to the sources. And so I'll write here derivative of this W low with respect to M and so if we take this derivative, we'll get something like the inverse of the matrix to the I guess it's just to the 1 over NC. Okay, so this is the expectation value of the Meson operators in these vacua. Okay, yes. Yes, thank you. Yeah, so yeah, thank you. Okay, so now we could try to interpret these expectation values of M in terms of some effective action. So we can write down an effective action as a function of the meson fields and lambda. Let me just write B1 to B3 NC minus NF. And so we could imagine that we have some effective superpotential. And now we're going to add trace of M. So here this trace is over the flavor indices. And then we could compute the expectation value of M that we get by just taking the derivative of this with respect to M and setting it to 0, setting the F terms to 0. And then we should get that same M that I wrote down over there. And so if we ask what's the difference between this thing, which depends on big M, and this thing that depends on little m, this is the usual thing that you have in field theory, that you can write an effective action in terms of the sources, and it's like a Legendre transform. It's related by a Legendre transform to some effective action as a function of the operators. So this is just like a Legendre transform. We take a derivative with respect to m, and we get this thing. And so since we know, so we get the expectation value of m, and also we get this W low as a function of m and lambda to the B1, which we know, it's the thing over there. And so now we could invert the Legendre transform. So this is inverting the Legendre transform, and what we get is that W effective is NC minus NF. Let's switch to a bigger chuck. Lambda to the 3NC minus NF over the determinant of M to the 1 over NC minus NF. Okay, so this is, you can check as an exercise. If I take this and if I add that, take derivative with respect to m and see where it's 0, you'll get the same m that I wrote down over there, and you plug that back in and you'll get this W low. Okay, so this is an interesting result, and now we can ask if it makes sense. And whether it makes sense or not depends on whether NF is bigger than NC or is less than NC or is not. So for I should say it always makes sense when the flavors are massive. So for massive flavors, this is always just perfectly fine. But now we could try to ask if it also makes sense when the flavors are massless. Okay, so now we want to study the theory with m equals 0. And again, this theory has a moduli space of supersymmetric vacua. And for NF less than NC, what we have is that if we write as a function of these meson fields, and we write down a potential V, then the classical theory has this moduli space of vacua where they all have zero potential. So this is the moduli space of the classical theory. And now when we turn on the quantum dynamics, we can ask what happens. And maybe I'll just write here that this is as a function of m, but we could imagine that we could give expectation values to m. What happens in the quantum theory is that there's this dynamically induced effective superpotential, which is this. And the reason why this is a good thing is now because we could add mass terms and we could reproduce these answers that we know are correct when we add the mass terms. The other good thing about the other way that this could be seen, which is how it was originally found by Affleck, Dine, and Seiberg. So when we set the masses to 0, this is, so here ADS isn't anti-de Sitter space, it's Affleck, Dine, and Seiberg. This is a superpotential that they showed in the case where NC minus NF is 1, this power here just becomes 1, and then this is the instanton factor. So this superpotential should be generated by an instanton. And this is a calculation that could be done to see whether or not there's an instanton superpotential. It's not obvious that there is one because the instanton, I drew it last time. It has all of these fermion zero modes. They're the 2NC Gaugino zero modes, and then they're the 2NF flavor zero modes. And in order to get a superpotential, you need 2 zero modes. And so it looks like it's way off from 2. But what happens is that when you give expectation values to m, some of those zero modes actually pair up. And at the end of the day, you have 2 zero modes. That's what Affleck, Dine, and Seiberg showed. And so there is an instanton that generates this for the case of when NC minus NF is 1. And then for lower NF, you can get it just by adding mass terms and integrating out fields. And so you can see that it's there for all NF less than NC. Actually, for NF less than NC, we could interpret it also as being basically just this superpotential. Because if NF is less than NC, then what happens is by giving expectation values of m, so maybe I'll just write it here, for NF less than NC, we have SU and C on this moduli space. We give expectation values to m, breaks to SU and C minus NF. And so we have a low energy theory whose gauge group is SU and C minus NF. And so now we can just write down, and that low energy theory has 0 flavors. So that low energy theory has exactly this superpotential, but in terms of the lambda low, and in terms of the low energy number of colors. So the low energy number of colors is NC minus NF. So that's this factor. And then the low energy lambda is exactly this thing, just by this matching that we did on the other board. So this is just lambda low, and it's divided by the number of remaining colors. So we could interpret this, so maybe I'll write it here. If NF is less than or equal to NC, then for NF is equal to NC minus 1, we get W effective is an instanton, which was shown by Affleck, Dine, and Seiberg. And so what that means is that we generate a non-zero potential. And this is a violation of the non-renormalization theorem. This was, people wondered if the perturbative non-renormalization theorem applies non-perturbatively, and here it's a non-perturbative violation of the perturbative non-renormalization theorem. And what it tells us is that if the theory has zero masses, we get this potential from, we can't really draw it exactly because the potential involves, so this V is like K, M dagger, inverse, the W dm. Let's just write W prime squared, where prime is derivative with respect to M. So this part we know behaves like this. If you look at how this thing behaves at m equals 0, it blows up. We don't know the Kähler potential, so this thing is a bit schematic. But what we have is a runaway vacuum. So the vacuum wants to go to infinity. And then we can stabilize this runaway by adding mass terms. And if we add mass terms, then we get these, if we add mass terms, then we get this formula. And in fact, we can see here that as we take these mass terms to 0, if NF is less than NC, these vacua go off to infinity. So there are some supersymmetric vacua at infinity, and it's just a runaway. So the classical theory had an infinite number of vacua, and then the quantum theory has, depending on how you count, either no vacua or NC vacua hiding in infinity. Yes? Uh-huh.
So for this NF equals NC minus 1 case, you can do an instanton calculation and get the lower flavors by decoupling. Is there any analogous, is there any kind of fractional instanton way we can think about the lower number of flavors and where that superpotential would come from?
Okay. Yeah. Thank you. Yeah. So. Yeah. Thank you. So the question was, so I mentioned that in the case of where this thing is 1, that it's an instanton, and so we can actually see how this is generated by an instanton calculation. So the question was, what about in the case where NF is less than NC, and so this is like a fraction of an instanton, and is there a way to kind of directly calculate that from some fractional instanton configuration? And yeah, that's a good and natural question, and it's not real. There's not really, I would say, a satisfying calculation of that, kind of directly understanding some fractional instanton configuration and how it leads to that. Yeah. So like for instance, if this thing is 2, then this would be like some kind of square root of an instanton. And yeah, there's not a satisfying calculation of that directly. Thank you. Okay. Yes. Let's see. So now we could try to go to more flavors. And we can see that this thing, if we look at it for instance, for NF equals NC, it clearly doesn't make sense because here I'm dividing by 1 over NC minus NF, and so I would be dividing by 0. So this thing clearly doesn't make sense if NF equals NC. So maybe I'll just write. So for NF equals NC, the reason why it looks here like we're dividing by 0 in this case is that determinant of M and lambda to the 3 NC minus NF have the same quantum numbers, including the anomalous symmetry when NF equals NC. And so we just can't form a sensible superpotential. If we want to have something have the right dependence under the anomalous U1, we need this power. Well, basically, to have the right dependence on the anomalous symmetry, we have to divide these two by each other. And then we're left with something that has R charge 0, and so there's just no way to form a superpotential with R charge 2. But what can happen, so in this case, W dynamical on the moduli space has to be 0 because there's nothing that can be written down. And then it looks puzzling how to get these answers when NF is less than NC. And this was resolved by Nadia Seiberg, who pointed out, who showed that the classical constraint that I mentioned last time, classically this should be 0. This classical constraint could be modified by an instanton in this case. And so this becomes lambda to the 2nc. This is a quantum deformation by an instanton. There are other cases, like in two-dimensional nonlinear sigma models, where you can have some quantum cohomology where an instanton modifies classical relations. Here it's an instanton correcting a classical relation. And so in this case, we just get a moduli space that's smooth. Unlike the case where if we set this thing to 0, the moduli space would have had a singularity at the origin. And so the classically singular moduli space is smoothed out by quantum effects. Now, for NF bigger than NC, there are similar classical relations, but they can't be quantum modified like this because the symmetries just don't allow it. This is very special to the case NF equals NC. So for all NF bigger than NC, no of the classical moduli space, because the classical moduli space will have some relations involving the mesons and baryons, and then in order to have a quantum relation, we need to have some lambda that changes it. And if you just look at the charges, under these charges, you see that there's just no way to do it, except for this case, NF equals NC.
Question?
Yes?
If you didn't know about supersymmetry and holomorphy but could do instanton calculations, does one know how to calculate this? So the question was, can this be directly calculated just from a straightforward instanton calculation without using special properties of supersymmetry? And this was there was a paper by Fennell and Pouliot that tried to directly do the instanton calculation and argue for this. Yes, in principle the answer is yes. Okay, so for NF bigger than NC, there's no way to modify the classical constraints, and so for NF bigger than NC, M quantum is M classical is singular. It's a space that has some singularities, and since there are singularities in the low energy theory, that means that there are some new massless fields or some new light degrees of freedom that are needed to resolve the singularity. And the other thing that's needed is that if we add mass terms, we should reproduce those expectation values of the meson operators that we have before. And so in a sense, if we add mass terms, we should get something like this. But this doesn't really this definitely doesn't make any sense for NF bigger than NC. Because if NF is bigger than NC, the sign of this flips, and so the meson is
determinant of M is upstairs and lambda is downstairs. And that kind of suggests that as you make M bigger, the quantum effects are getting bigger, which I said at the very beginning, giving expectation values to M should make the theory more weakly coupled. And so the M is in the wrong place. It's in the numerator instead of the denominator if NF is bigger than NC. And also classically, the determinant of M would just be 0. Because if NF is bigger than NC, you get this M by multiplying Q and Q tilde. And there are only NC color indices. And so that's a matrix whose rank is at most NC. And so this matrix classically has rank at most NC. And so then if you try to take the determinant of that as an NF by NF matrix, you'll just get 0. So in a sense, this makes, this can't possibly make sense for NF bigger than NC. But the way that it does make sense is in terms of Zeiberg duality. And Maddie just walked in, so timing is perfect. So the idea is to interpret this in terms of another theory. So maybe I'll write the other theory over here. So the dual theory has a gauge group which is different. It's SU NF minus NC. So it's an SU NF minus NC theory with NF flavors. And a superpotential, well, plus, so let's call the flavors Q and Q tilde, and let's give them some flavor and color indices. Plus some extra gauge singlets. And the number of these extra singlets is NF squared. And usually the singlets are just called M because we're going to map them to the Meson operators. But for the moment, instead of calling them M, let me just call them phi. So there'll be some singlets F G tilde plus the superpotential. Okay, so that's the dual theory. And so again, we could make a table of all of the fields and their charges. I'm kind of tempted to put it on this table, but there's no room. Okay, so we have this. Let's call it SUNC tilde for the dual. So that's the gauge group, and then the flavor symmetry is SU NF left, NF right, if I wanted to, I could include the anomalous U1, but it's not going to play too much role here. And so we have these matter fields Q, which are in the fundamental here they're in the SU and F bar. They don't transform under this one. The baryon number is 1 over NC tilde. And the R symmetry, it's similar to the R symmetry over there, but I just substitute NC tilde. So it's 1 minus NC tilde over NF. So that's Q. Q twiddle is in the bar. These are all just what you would expect. And this phi, it's a gauge singlet. It's in the bifundamental of these flavor symmetries. It has baryon number 0 and let's see. Okay. Now, the interpretation of this duality depends on what NF and NC are. So
We're trying to make it super potential.
So it's NC over NF, right?
yeah, so the question was if I made a mistake here.
Because you want to map a phi to less than just an inch.
Yeah. So the phi should have actually the same charges as over there. So it's 2, yeah, thank you. Yes, indeed, this was my next point, was that it had the same charges, but thank you. Yeah, so there was a typo. And right, so actually let me emphasize that. So we want to be able to let's first check that these charges make sense given the superpotential. So this superpotential should have R charge too. So the charge that I want for this plus these charges should add up to 2. And so you can check that these charges will add up to 2. So that plus that should be 2. Yes, indeed. And so one of the checks, so the checks of the duality, maybe I should just write here. Okay, so the checks are that they have the same, the first check is that they have the same global symmetries. So we'd like to argue that these theories are related to each other in some way, and they have different number of gauge fields, but that's okay because a gauge symmetry isn't really a symmetry, it's just a redundancy in our description. And so we could use different redundant descriptions, that's fine. But the global symmetry should be the same. So they have the same global symmetries. And now we could try to map operators across the two sides, and the operators should match with their global symmetries. So the operator map will be, for instance, this meson operator is basically some Actually, let me write down this normalization that I like. There's some minus signs that work out nicely if you assign them this way. Where here H, let's put here H is some Yukawa coupling. So this superpotential looks like is a cubic interaction, and so sometimes I'll refer to this as like a Yukawa interaction. So this H is some Yukawa coupling. The normalization factors don't really matter too much, but there is some relation between the two duals, which is nice if you assign things this way. The important thing is that the meson operator is proportional to this FG tilde, and so they should have the same charges. And so this was what was pointed out, that with NC tilde, we want this to be NC, so it matches over on the other table.
And that's lambda of the dual theory?
I could write a lambda of the dual theory. Here I'm choosing the lambda of the dual theory and the lambda of the original theory to be the same, which we can make a choice like this. Yeah, so there are powers of lambda that we need based on dimensional analysis. Like here we take this phi to be dimension 1, and this meson has classical dimension 2, and so we need some lambda like that. In the quantum theory, the operator dimensions will actually be determined by the R symmetries, and the R symmetries match, so everything will work out in the end in terms of the operator dimensions. The other map between the operators involves the baryons, and so we can have baryons which in the electric side go like Q to the NC. Maybe I'll use this notation, like a wedge NC. What I mean by this with a wedge NC is that we contract the contract the NC colors with an epsilon tensor. And so we contract this with an epsilon tensor, and so it's completely antisymmetric. In terms of the flavor indices, it's like in this representation where there are NC boxes under the SUNF flavor symmetry. So we take the fundamental to be in the fundamental of the SUNF left, and now we're going to anti-symmetrize that NC times. And this thing maps to lambda to some appropriate power. I'll just leave this for you to work out, times little q wedge NC tilde. And so you can check that it's in the same representation of this SUNF left. This is a check that the operator symmetries match. And you can also check that they have all the same symmetries also under the R symmetry and under baryon number symmetry. So this thing has baryon number. This thing has, the way I normalized it here, this thing has baryon number 1 and this thing has baryon number 1. Okay, another check is the 't Hooft anomaly matching. So if there's a relation between these theories, then, and I should spell out more carefully what the relation is between the theories, but their 't Hooft anomalies should match. And so we can check that the various 't Hooft anomalies match. So we can check like trace of SUNF left cubed, for instance, should match on the two sides. So let's just quickly check what's that one. So SUNF left cubed on this side is NC from the Qs. And now we could try to check it on this side. And so on this side, there's a contribution from the little q's, but they're in the NF bar, and so that has a minus sign. And so this is on the electric side. On the dual side, there's a minus NC tilde. Plus, there are the contributions of these phi fields. And these phi fields are in the NF, and so they contribute with a plus sign, and there are NF of them. And so we get plus NF. And so if we flip this around, this tells us that NC tilde has to be NF minus NC. Okay, so that's a check. And now we can check other ones. We can check, for instance, I'll leave it as an exercise if you want to check them, but we could look at, for instance, trace U1R is a pretty impressive check. And if you look at trace of U1R cubed, this one is when you work it out, it's very impressive. You have to remember to subtract 1 from all of the chiral superfields to get the fermion component. And so for instance here, we'll subtract 1. The fermion has this charge, minus NC over NF. We cube that. We add, and we account for the fact that there are NC and NF of them. And then we do the same thing for this one, the same thing for here, and add it all, cubing all these numbers and add them together, and then do the same thing on the other side, and you can check that the two agree. But when you actually work it out, it's impressive to see how it works.
Is that minus 1 just do U1?
Oh, yes. That is a strange typo.
Our symmetry index.
U1R cubed. Thank you. Okay, so this is something that you can check. There's a whole long list of these 't Hooft anomalies. Okay, so I intentionally didn't erase this formula because I wanted to say how this is reproduced. The way that this is reproduced is that we can see here that if this phi, which we interpret as the meson operators, gets an expectation value, it gives masses to these dual quarks. And so now these dual quarks have masses. And so then we can interpret this the way we can interpret this as if we gave generic masses, we would say that we have some W low in the dual, which is NC dual times lambda low, let's just put a tilde for now because it's in the dual theory, to the 3 NC dual 1 over NC dual. So NC dual is NF minus NC. And then this lambda low to the 3 NC dual is the determinant of this mass matrix, which is this H times phi. This is our matching relation, and then once we map phi to M, we can reproduce this answer. Okay, so that was right. So if we just use this matching relation, we can show that these two things agree. So, right, so this thing has an interpretation in terms of gauge-Eno condensation in the dual theory. Any question?
Yeah, that form of physical potential NC tilde, that looks just like one that you wrote before, except for zero flavors.
That's right, yeah. So the idea is that if we move along the moduli space from the dual point of view, when we move along the moduli space, we're giving expectation values to this phi that we map to the Meson operator. And so for generic expectation values for this phi, all of these Q's are massive. And so the low energy theory on the dual side has zero flavors. And so I forgot to repeat the question, but I think the question was just that this is the theory with zero flavors. That's right. So this is, if we give, the way that we can interpret this is if we give expectation values to M, then we integrate out the dual flavors, we get something which is like zero flavors in the dual, and then that gives this superpotential. So, and another point is that in the dual side, so I mentioned that this meson matrix has rank at most NC. It has rank at most NC along the moduli space of vacua. But from the dual point, what the dual shows is that actually you get all NF squared components of these things. And it's only when you try to give expectation values to them, eventually you generate a superpotential that tells you you can't violate this condition on the rank when you give expectation values. But if you don't give expectation values, if you're just at the origin of the moduli space, all NF squared components of them are actually there. Okay, so what's the interpretation? So for so on the electric side, what happens is that okay, so if NF is bigger than 3 NC, the theory is in the free electric phase, where it's not asymptotically free. As we go towards the infrared, we just get the free electric theory. Then there's a conformal window. Here I'm plotting this as a function of NF. As we lower NF, there's a conformal window where the theory is asymptotically free. And then what the dual tells us is that something special happens when the dual theory is no longer asymptotically free. And so the dual theory is no longer asymptotically free when NF is equal to 3/2 NC. And when we reduce the number of flavors below, so here, if we look at when this theory is asymptotically free, the one loop beta function here is 3 NF minus NC minus NF. And so what we see here is that this thing has the way I wrote it, the sign for asymptotic freedom would be if this is positive. So this thing is positive as long as NF is above 3/2 NC. But then when NF is 3/2 NC, this thing becomes 0. And as NF goes below 3/2 NC, this thing has the wrong sign. And so it's not asymptotically free. So in this range, what happens is that the magnetic dual becomes free. So it's free free magnetic dual. So this is from the point of view of the electric side. And from the point of view of the magnetic side, we would draw a similar table as a function of NF. And so we would say here that when NF is 3 NC tilde, above that it's the free magnetic. Then all the way down to NF is 3 halves NC tilde. We have a conformal window. And then here below that it becomes the free electric theory. So what happens is that this phase, the free electric phase, we could get that as like a strongly coupled description of the magnetic dual. We could get this free magnetic phase, which is up here, as a strongly coupled description of the original electric theory. And then there's this conformal window where we can use either description. So the picture to have is that in the conformal window, where NF is between 3 NC and 3 halves NC, both of these two theories are asymptotically free. And so we could start off with either the electric theory, which has the SUNC, or we could start off with the magnetic, which has SUNC dual. And in our renormalization group flows, these are two different ultraviolet starting points. And these are two different free ultraviolet starting points. So we can have this free description, or we can have this free description, and then in the ultraviolet, and then for both of them, the couplings are asymptotically free. And so the idea is that in the infrared, they flow to the same superconformal field theory, which we could use either description. So this is an example of an infrared duality. The two theories are definitely different in the ultraviolet, and then they flow to the same infrared fixed point. So the interpretation of the 't Hooft anomaly matching that I mentioned that you can check in detail is that the 't Hooft anomalies are constant along both of these flows. We could compute them up here in free field theory, and we could compute them here in a different free field theory. And then by the time we get to the infrared, we can't really directly compute them here except for by using a 't Hooft anomaly matching. And so here they should match because we have the same global symmetries. So this superconformal field theory has various properties that we know because they're constant along these renormalization group flows, like for instance a 't Hooft anomaly matching. Another thing that we can check for these RG flows is the A theorem. And so we could compute here like A UV on the electric side. We could compute here also A UV on the magnetic side. And then here in the superconformal field theory, we can compute A in the infrared in either description. And I'll write down in a second the way to compute it using the 't Hooft anomalies. But the reason why it matches is in these two descriptions is because the 't Hooft anomalies match. So this is the interpretation of the duality in the conformal window. The interpretation outside of the conformal window is in a way even more dramatic. So this is interesting that the conformal field theory can have different descriptions. And if you want, you could kind of think about this as a statement of universality, that there are different renormalization group flows that can end up at the same fixed point. But the nice thing about this universality, which is another one of the checks, yes, actually maybe I should just mention here before I forget, we can also as a check study the deformations and so on the electric side we can add a mass term or we can give an expectation value to m, and so this is on the electric side, and then on the dual side what we can see is that an expectation value of the meson operator, this is like what I said before, it's giving expectation values to this phi which give masses to the q's. And so from the dual point of view, this m is like a mass term. And also we can see on the electric side, if we add a mass term for a meson field, in the dual side, what we'll be doing is we'll be adding a term here plus m phi. And now the phi equations of motion will force q and q tilde to have an expectation value. And so here the mass term, so this is a mass term for q and q tilde, and here this thing maps to an expectation value for q and q tilde. So we exchanged these two under duality. And again, this fits with exchanging strong and weak coupling, because mass terms take you to stronger coupling in this description, whereas here in this description takes you to weaker coupling. And here this thing takes you to weaker coupling in this description, and here it takes you to stronger coupling in this description. So even though it's a statement of universality, it has some interesting way of flipping strong versus weak coupling. Maybe I should go over here.
About 5 minutes left.
Okay. Okay, I kind of said it in words, but maybe I'll anyway just write the interpretation in the free magnetic case. So for NF less than 3/2 NC, the interpretation of the duality is that we have the electric SUNC theory in the ultraviolet, and that theory is asymptotically free. So this is a free ultraviolet fixed point, and then we RG flow, and we end up with the infrared free magnetic dual. And so the surprising thing here is that the dual description has these infrared free gauge fields. So from the dual point of view, the low energy theory has this SU and F minus NC gauge group, whose coupling is going towards 0. And so those theories, those fields just become some free gauge fields in the low energy theory, which are somehow composites of the original ultraviolet theory. So this is some kind of composite gauge theory. Okay. Let me just finally write down the formula for the A anomaly. So the A anomaly in a superconformal field theory it's some linear combination of the U and R at 't Hooft anomalies. So we could compute this in the infrared conformal field theory. We can also compute it in these free electric phases, and we can check the A theorem that in all cases A infrared is less than AUV, and now I have to decide if I want to say more about this in the next lecture or go to higher dimensions in the next lecture. Yeah, so maybe I don't know if I should take a poll or just decide. Yeah, so there's much more that could be said about if, for instance, how this R symmetry is chosen, how it evolves along the renormalization group flow. This R symmetry is the R symmetry in the stress tensor multiplet, and so we can ask how can it possibly be that A in the ultraviolet and A in the infrared could be different, and the way that happens is because the R symmetry kind of changes between the ultraviolet and the infrared. And there are cases where we have to use something called A maximization to determine the right R symmetry. So there's much more that could be said about using this formula and connect it to 4D theories. My original plan was to finish all of that today and to discuss tomorrow 5-dimensional and 6-dimensional conformal field theories. So maybe just for fun, I'll ask for a poll. Who votes for 4 dimensions and who votes for 5 and 6? How about 4 dimensions? Okay. What about 5 and 6? It's almost even, but maybe a slight preference for 5 and 6. Okay. Well, it'll be a surprise for for all of us. Yeah. So tomorrow I'll do one or the other. Okay, thanks.
I have a question.
Yes.
So on the first day you talked about, non-supersymmetric QCD, and you wrote sort of a diagram where you talked about how it has a non-asymptotically free regime and a conformal window, but there didn't seem to be anything like this free magnetic phase, right? Even as you vary the number of flavors. And it's such a surprising thing to have these composite massless gauge fields. Is that something that you would expect to exist without supersymmetry? Could we cook up, could Tom cook up some other theory with some number of colors and flavors and find such a thing on the lattice?
Yeah, so just to repeat the question was, this case where you flow to an infrared free magnetic dual seems very surprising, and how special is that to supersymmetry? Could there be non-supersymmetric variants of that? Could it be found on the lattice, for instance? And how special is it to supersymmetry? So I don't know the answer to that, is how special it is for supersymmetry. And certainly you could try to add some small supersymmetry breaking terms and see what happens. And then in general, you kind of lose control as you try to decouple the extra supersymmetric things. We could try to just decouple the super partners here and go to ordinary QCD. But at some point, you kind of lose control when you turn on the supersymmetry breaking. And so it's... The answer to the question is I don't know. I don't know if there's a non-supersymmetric version of this, but it definitely looks very exotic. Coffee. Tom is saying time to finish for coffee. Okay.
All right, let's thank you again.
Thank you.